So a quick thank you to Bill and to Napier for hosting us. As Bill mentioned, my name's Stephen Hampton. I'm the CTO at Hutchinson Networks. A little bit more about us in a few minutes, but I want to get onto the detail of the slides. So I realize it's late in the afternoon, so feel free to have a little snooze if you need to. I know what it can get like in the afternoon. So when Bill asked us to talk, we're essentially the infrastructure guys at the data scientist application developer conference. So we maybe do something a little bit different to most of you. So it's traditionally networks, network security, server build, virtualization, etc. So when Bill said about speaking at the event, there was a couple of things I thought we could talk about. We could talk about how we use big data and how we use analytics in the network and how it's going to change how we use the network. And that might be interesting to people. Now, if you're coming from a big data background, though, what might be more useful is how you should be building networks, or the people who are building networks for your big data solutions, what those should look like. So traditional networks we'll have a look at, but have some shortcomings around big data. So the agenda for this one really is to look at big data solutions, how they map to the infrastructure, look at traditional networks, see some of the shortcomings, and then look at how we do SDN fabric type networks these days, and how that fits the big data solution a little bit better. So I just wanted to start with an example of big data. So the one we'll be mostly familiar with will be Hadoop. So Hadoop's based on HDFS, the Hadoop distributed file system. So as soon as you see the word distributed, you know that it's going to be spread across an infrastructure. When it's spread across an infrastructure, you need a network to connect it together. Where you've got a network, you need to secure it. So if you look at the components of that, two first key building blocks. There's the name node. The name node is responsible for storing the metadata, distributing the blocks, and really kind of mapping things out. The data node is the one that actually does the processing. So if you take your distributed file system, what it's going to do is take in a big data set, spread it across the network, do some of the computation, and bring it all back together. So, and again, I may be teaching people to suck eggs here, but if you just bear with me for a few minutes. I'm just going to sort of scroll these out. So if we look at the places where this really impacts our network, when we start off in the initial instance, we've got to get the data into the system. So that's our initial input data, our structured data, or unstructured data, whichever it is. After that, then we start working through a map, shuffle, reduce output process. So in the mapping stage, you're taking that name node, and if, for instance, you've got, I don't know, a data set with 100 million records, and you've got 100 nodes that you want to split that across, then you'll do some mapping and you'll take a million records and spread it out across all of your data nodes. That stage is called shuffle. Then when they get the data and actually do the processing, that's called reduce, and then we move into the output. And then finally, at the bottom, you've got the reading of data. So where these bits actually hit the network, the initial write application, like I mentioned earlier, the data's coming in, it's coming into the network, it's coming into the infrastructure before you start mapping it out and doing something with it. The map phase, there's very little that's going to go on the network here because you've got your name node, and the name node is going to figure out how it's going to map the data. The shuffle, though, at this point, we're distributing it across those data nodes, the ones that are going to do the processing. So at this point, we've got a big push. We've got a lot of data going out over the network. Reduce, again, that's mostly done with on the data node, and then the output replication, again, your data back on the network. So at this stage, two things should be obvious. One is probably that I've come to the depth of my knowledge on big data, so I'm not going to go too much further on that. But the other one is that we get big chunks of data for a short period of time, and then it disappears again. So from a network point of view, we're looking at something that's bursty. So we don't need too much bandwidth, and it goes quiet, and then all of a sudden we get a big push, and then it goes quiet again. So we need networks that can deal with that. So if we look at some of the characteristics that we sort of typically talk about with networks, I'll just go straight to the second one because I think that's potentially the most important one. I mentioned it, bursty traffic. So on a network where you've got bursty traffic, you need low oversubscription rates. You need big queue depths. So the queue depth would be, for instance, if you're the receiving interface on a network and you've got lots of data, or say it's the sending interface, you've got lots of data being sent out through that, but you've got a 1 gig interface and you've got 1.2 gigs going out over it, then you want to store some of that data in queue, in the buffers, on the switch, so that it can send it. So you want nice queue depth, you want low oversubscription ratio, so you're not throwing, say, 48 1 gig servers all into a 48 port switch and then going up on 2 gig, then you're 1 to 24 oversubscribed. So the queue depth and oversubscription is very important. To jump back to the first one, availability I think is pretty key as well. You know, again, if you're talking about 100 data nodes, your network segregated into a typical hierarchical model, then if you lose a portion of that network, you could lose 30% of your data nodes, and all of a sudden your ability to process has gone way down. We talk about latency a lot. It's sort of a slight bugbear of mine that we talk to a lot of customers who are immediately, I need a low latency network. It needs to be really low latency. If you look at how we sort of push networks these days, you're talking about a 5 microsecond port-to-port delay on some new switches, and some will be sub-microsecond. The microsecond is a millionth of a second. So in an environment, a big data environment, you're looking at spreading your data out to the data nodes, which are then taking several minutes, or in some cases maybe longer or hours, to process the data. So if your data is getting there in 20, 30 microseconds rather than 5 microseconds, it's really not going to make much of a difference. So I think latency for me isn't as much of an issue. What can be an issue, although there's some debate over this one, is jitter. So jitter is variation in that latency. So that means that the two same packets go at different times. One is going on a congested link, stays in the buffer a little bit longer, and takes a little bit longer to get there. So where you've got highly synchronous workloads, where you're expecting them all to process all your data nodes, your 100 data nodes across that big data set that I mentioned earlier, where you're expecting all of those to process the data at the same time, then if it's getting there at a different time, then that can be an issue, because sometimes jitter can be up to 2-3 seconds if you've really got a slow link and very oversubscribed. But again, depending on the sources that you look at, some people think this is important. In some cases, it hasn't been too much of an issue. But latency, definitely, I don't think we need to worry about. Scale, certainly, I'm sure throughout the day you've been bombarded with the number of zettabytes that we've got going across the internet, the number that we've got in the data center, how much storage is going to grow, et cetera, et cetera. So basically, we're creating and consuming more data than we ever have been, and that's not going to reduce, it's going to increase. So the ability to scale up your environment very quickly is going to be important, because that 100 million records in a data set today may be a billion tomorrow. Security and multi-tenancy. So where you've got different environments, say a PCI environment and a non-PCI environment, then having separation of these is important. You can go and buy one set of hardware for your PCI and another set of hardware for your non-PCI, but that becomes very expensive, especially now if you kind of think you need to spread your multi-tenancy a little bit wider than that, then you're buying physical pieces of hardware everywhere. I really think we're into the age of virtualization everywhere, not just on server, but also on network. And Bill mentioned the F5. The ones that we're using are actually virtual editions, so they're appliances, load balancers that run on a VM. And if we need more bandwidth, then we just increase the license, or we spin up more instances of them. But security and multi-tenancy are very important. Performant. So 10 gig interfaces on server chassis are nothing new. In fact, you've probably got multiple 10 gig interfaces coming out of them. I think what we're likely to see over the next couple of years is 25 and 50 gig interfaces, which are strange numbers because, for a while we've been talking about 10, 40, 100, but we're now starting to see switch vendors come out with 25 and 50 gig switches, because that's what they're expecting the server market to move to. So, when you start looking at your access and your backbone, then these are the things we should consider. So just to take you back a little bit, And again, apologies for the sort of the network bias, but it's what we do. This is a traditional network architecture. It was called the hierarchical model, and it's basically a set of core switches, a set of distribution switches, and a set of access switches. What you do is you connect it all up in a resilient fashion, and then, due to the beauty of Ethernet, you shut down half the links. So all the dotted lines are basically out of action. So you have something called layer 2 loops, which will crash your network. So you use a protocol called spanning tree, and that shuts down every redundant link that you've got. As a result of that, you're losing at least half of your bandwidth, or possibly more, depending on how you've engineered your network. So that straight away is a problem. You do have redundancy. So if you lose some links or if you lose some switches, then things carry on working. But because of this spanning tree, you've actually got to stop it for 4 or 5 seconds before it kicks off again. So you've got a delay in the time it takes to fail over. You've potentially got a lot of oversubscription. I may have exaggerated a little bit because I've got 1 gig links between the access layer and the distribution layer. These days you probably will have 10, depending on what your budget looks like. So you can scale that up a little bit, but we'll see in a moment it's not the best way to scale. And then right at the top we've got a set of firewalls. So if you again say PCI, non-PCI, then everything that's going between those two areas, you need to pass through those firewalls. And a fundamental rule of networking is the firewalls are always going to be slower. And the reason why they're always going to be slower is on the switches, you look at the MAC address. On the routers, you look at the MAC address and the IP address. And on the firewall, you look at the MAC address, the IP address, and the port number. As a result, you've got to read more data, you've got to do more with the packet, so it's always going to be slower. So if you've got big appliances, you can push 10 gig interfaces into them, but as you start doing more security, they're gonna slow things down. So these, like I mentioned, this is how we used to do it, and I think in terms of what you're looking for big data, it's got a few challenges. It doesn't scale so well. We don't have the same amount of throughput. In terms of bursty traffic, because we see a bit more oversubscription, then it's gonna slow that down. It's not gonna scale easily. So. All the rage in data center networking for the last few years has been network fabrics. So network fabrics take away a lot of the traditional networking problems. So if you come right down to the bottom, firstly, where we've got our server clusters. So essentially, think of these as your server chassis, and on those you've got your name nodes and your data nodes. You've got your Hadoop distributed file system on them. This is where the individual nodes live. Firstly, we've got 2 solid lines. That uses something called equal cost multipathing, which allows you to take 2 links or multiple links out of the server chassis, bring them up into 2 different switches for resilience, and actively use both of them at the same time. That means that one flow goes left, the other flow goes right, and then it uses a hashing algorithm to decide which ones go where. So that's the first thing we get. Now, if you look at the topology, it's a lot flatter. This is called the leaf and spine topology. It's based on something called the Kloss architecture, who was a mathematician way back when, I can't remember exactly. But so he came up with Kloss architecture for a while. We've been using it for years, by the way. Your telephone system is all based on Kloss architectures. But the idea is our leaf switches, we don't connect them together. They exist solely, our spine switches exist solely to connect together our leaf switches, which are the ones across the middle row. Now what we have is a 40 gig fabric that effectively looks like one. So we've taken away all the spanning tree, we've taken away the traditional Ethernet, and we're going hop to hop between any 2 leaves is just one hop in through the spine and back out again. So that means our latency is completely deterministic. Also in there, we've got multiple 40 gig links. So again, if you go back to leaf switches with 48 sort of ports all connected at 1 gig, then you've got 80 gig upstream. If you're connecting them at 10 gig, then you just run out more 40. These will support think about, in some configurations, about eight 40 gig ports each. So the amount of bandwidth you're getting up to your spine is a lot more significant. So in terms of scale, well, we want to scale this out. We just keep adding on nodes, and you keep adding on clusters at the bottom, and you keep adding on data nodes, and you therefore make your calculation of the big data a lot shorter. Security is an interesting one, and Bill mentioned SDN. That wasn't in the plan. I've broken it. So Bill mentioned SDN earlier. So with software-defined networking, what we're doing is we're taking a lot of the control plane for the network out into software. So the little box in the middle of the cloud is a controller. What we do is we create all of our policy around how we forward traffic on the network in there. So when we add another leaf switch, we don't need to do a whole bunch of configuration and configure every point like we used to. We do it all from there. And the other thing that's quite exciting is there's no firewall on this diagram. So in a lot of SDN architectures, you start off with a default deny. You don't permit traffic to go anywhere unless you have a policy that says you can. So essentially, we've certainly moved away from having a DMZ, a demilitarized zone at the side. What we're effectively saying now is the entire network is split up into sections, and all of those are DMZs. They're all secured from each other. And if you do want, and with this architecture as well, you can use simple things like contracts, just say A to B, or you can insert an F5 virtual edition device into the middle to do some load balancing or web application firewalling. And the vast majority of these architectures are also built to scale. So, you're talking about swapping out a line card to introduce 100 gig, or a lot of them have innovation around universal ports, where the port will support 100 gig, 40 gig, 10 gig, 1 gig, and you swap out the transceiver depending on what you need. So this is the way we do it these days. And if you haven't guessed already, we've got one of those. And it's something that we've been building for the last year. It's what our Fabrics and public cloud infrastructure is based on. But we also do work around building network fabrics for our customers. In the data center space, it's very much where we see things are going. So I think little message is, if you're doing big data and you're thinking about how you're going to do big data, then you're going to be doing it on your own premise, or you're going to be doing with a cloud provider. In terms of doing it, and either way, you're looking for a set of characteristics. The underlying network should be based on a modern network fabric, not based on traditional spanning tree Ethernet. Things like equal cost multipathing, you should be looking at 40 to 100 gig support between your leaf and spine, or the core of what the fabric is. You should be looking at a minimum of 1 to 10 at the edge for connectivity down to servers, but possibly future for 25 and 50. In terms of how you're going to control policy, it should be software defined, and how you're going to bring in appliances to do load balancing, firewall, web application firewalling, etc. You should be looking at NFV, which is network functions virtualization. It's essentially a network appliance, your IDS, your router, your firewall running on a VM, and placed logically into the network using VLANs and VXLAN. And look for things like secure microsegmentation. The secure microsegmentation is I mentioned earlier about the default block and allowing us to sort of build up all these DMZs. Right, and I mentioned right at the beginning that I wanted to talk about the infrastructure that you need to build big data on, but I didn't want to leave out the other stuff, so I just made a quick note of sort of 4 points of areas where I think big data can actually help what we do as network engineers and network architects. Some of these are obvious, but we'll just talk about. I'm not going to talk about SIM because we've heard from Splunk today, and I think you've probably heard from 1 or 2 other vendors as well. But obviously, in the area of security and incident event management, we've got lots of data. we don't know how to handle all that data. We need to figure out a way to do it, get good information, get rid of the false positives. So that's going to be a big area. Infrastructure analytics and troubleshooting, you can take that on a step. We work with a storage vendor, Nimble Storage, who basically built their platform with a clean sheet of paper maybe 5-6 years ago. What they immediately did was their storage arrays talk back to the cloud, and in the cloud they take all the analytics. If you're running out of disk space, you're running out of IOPS, they'll automatically order you a new disk and send it to you. If you're going to have if it thinks that the analytics are showing that you're going to have problems with your array, then they'll prompt you and tell you that you've got an issue. The last one, though, I think is particularly interesting. So within the SDN space and within our Fabrics platform as well, we automate everything. So the aim is for the entire environment to be automated. But we need to bring the intent to that automation. So when we work with a customer and they say, I've got a web, an app, a DB, and I want a firewall between them, and I want a load balancer every layer, we need to understand that the logic is that we push a firewall there, we push a load balancer there, we build out a secure network. That intent comes from us. Intent-based automation, this is essentially hooking up the automation with some sort of big data analysis that tells us what the intent should be. And that could be troubleshooting. I think somebody mentioned earlier we don't want to go and remove Skype from everybody's desktop, which of course we don't, but we can't not do it for that reason. What we need to look at is somebody's being attacked. The way to block that attack is to block an IP address at the edge. Now, if we can take that information and put it into our automation, then we cut, well, all of us out of the middle. So I'm not sure what that leaves us doing, but you get the idea. But intent-based automation, I think, is going to be really important for networking. And that is, that's it.
So thank you very much for that. Hello? Yes. Okay, so thank you very much for that. Do we have any questions? No questions? Yes, okay.
Probably take the microphone when you have to answer.
Hi, Steve.
Hi.
Looking at that model you had up there, I guess that's predominantly aimed at a data center core,
Yeah.
distribution access layer. Do you have any method to choose how to scale it?
How to scale it?
Yeah, that'd be my first question, and then the second one would be, you didn't mention how you would track flows. Okay, data flows to feed the big data. So you'd have big data that is used for something, but the network itself creates more big data. So how do you deal with this?
Okay, so let's just do the first one. In terms of scale, in a leaf-spine topology, it's relatively easy because you're adding on more leaves to scale out your pods. So if you think the spine could be a 16-slot switch with up to 48, 40 gig ports in the middle of it. So for every one of those, you can connect on a leaf switch. Now, if you're using an SDN overlay on the top of that, you don't actually apply any configuration to the edge ports on those. You apply the configuration to, say, for instance, a VM port group. So if that port group can then move anywhere on any of those leaf switches and keep the same policy information. So in terms of scaling it, you just keep adding on leaf switches. And you keep the flat topology, you keep the one hop between any two devices and the deterministic latency, and you keep your configuration, your policies almost identical. Then the second question was, was the network was the network choosing the flows, and so and then.
When you use network topology to scale to that size,
Mm-hmm.
okay, you're talking low latency, high throughput, and scalable.
Mm-hmm.
And then we're likely to want to see the flow output of net flow symbol to tell us what the network did.
Yes.
Did it transfer, and was it right or wrong?
So the and I'm not going to go sort of product dropping here, but the product that we work with has contracts between all the different areas, and each of those contracts is a window into the traffic. To give you an example, we're connecting our ISP through to a virtual router, and we could just put them in the same group that allows them to talk to each other, but we put them in different groups because that allowed us to put a contract between. When we put a contract, then that means that we've got visibility of every flow that goes through those 2 points. So anywhere that you've got that sort of contract within the SDN solution, you've got visibility of the flows that pass through it. Now, if you, rather than the contract, you could have an appliance, and where you've got the appliance, you'll be reliant on the analytics from that appliance. So if it's, if it's an F5 LTM, for instance, then you can feed the logs out elsewhere. Also, the solution that we're working with has health scores based on applications, so you can trace any point in the fabric to another point in the fabric, and it will map out the path for you graphically to say this is the route it's taking, whether it's just from within one leaf and one group, or between different groups and through a contract or through an appliance. So you've got that that visibility in there again. And I also, we're also talking to vendors who are looking at taking flow analytics beyond NetFlow. Into big data tools, basically deduping the flows. So you've got God knows how many of that kind, and you just drop it. So I think that will help with that as well.
Okay, thank you.
Okay, thank you very much.
No worries.
So yes, thank you.